Hi, my name is Ricardo Moreno, and this is my presentation for the Doctoral Meetings 2026. My thesis, which is supervised by Marco Raiola and Luis Aspicueta, is about aircraft jet noise diagnosis using massive microphone arrays. I belong to the Experimental Dynamics and Propulsion Lab, and my work has been mainly funded by Jamaica Project and Influentia Project. To give you some context, this is an aircraft traffic map where you can see blue and red lines correspond to landing and departures. Basically, takeoffs generate more noise than landings, and this is because the aircraft needs more power engine. By using microphone and some algorithms, beamforming algorithms, we can localize and determine the position of these noise sources. But mainly, during the takeoff, we can identify the fan and the noise and the jet. They both contribute the most to this noise generation. If we analyze the dynamics of the jet, we can identify these main four components: the potential core, the large and fine scale structures. They both are responsible for this noise generation, but mainly the last and this is the most important, which are the wave packets. They generate the majority of this acoustic energy because they are more directive, and actually it's what population hears. As you can see in this picture, these coherent structures are traveling downwards, and they are evolving and also somehow being modulated. In this animation, you can see, mainly in the second animation, you can see this amplitude is not only evolving in space, but also is being modulated. So this is a complex noise source whose topology is very dynamic and complex to determine as a static noise source. So we need microphone arrays if we want to represent noise emission with images. And what we have implemented so far is a massive microphone array, just considering what we have in the market, what the hardware limitations, and also a very tight budget. So we have this developed this microphone array inspired in this underbring design that it's supposed to be non-redundant between microphone distances, also considering what's the aperture that the whole microphone array will have, where it's going to be placed in the anechoic chamber. We have also some geometric limitations, such as the cutoff frequency. It has to be aerodynamically transparent because since we are working with jets and airflows and this kind of stuff, we also must consider these criteria. And also we have run some simulations just to be sure that the sensor distribution, the performance of this configuration will be the best as we can. And we run the simulations along the frequency range, and we could determine the parameters of the spiral. This is what we have, the MX array. MX, because it is modular, multiplexed, MEMS-based. It runs on an embedded Linux system. It's scalable. The most appealing characteristic is that it's around €8 per channel. It is PTP synchronized. It's very precise. It's easily commanded by MQTT protocol. It has a very low latency because it uses a preempted real-time kernel patch. And well, this is the architecture of the MX array. Basically, what we use a microphone that allows us to concatenate 16 channels through one single data line. This is the architecture of the Big Album Black. We use four serializers, gathering 64 microphones. And this is the general architecture. So we have 16 modules. Each module handles 64 microphones. and everything connected to a network switch, which has a very particular property that it has a transparent clock, uses the PTP protocol, and by using the MQTT telemetry, we can command from the computer the acquisition, and it programs to each node with a countdown, so the acquisition is very precise. Also, we use a pulse injection with an additional Beagle Black if we want to synchronize with other systems, with other equipments. Now that we have the MX array, we want to identify these wave packets because they are responsible for this noise generation. This is our measurement setup. And we have the PIV cameras that captures the near field. And of course, a subsonic jet that is a jet that is in scale with 1 centimeter of the diameter, and everything within the anechoic chamber. So this is what we have with the PIV, just to give you an idea of the region that we are capturing with the 2D snapshot that this PIV camera measures at 8 Hertz, while the MX array captures at 8,000. Remember, we measure the MX array in the far field, and the PIV captures the near field. Since we have these loads of data, it's mandatory that we use some data compression. As I said at the beginning, the HPOD, the Hilbert proper orthogonal decomposition, is the one that fits the best for the PIV, and our first attempt would be to apply this to acoustic data. Well, it has some advantages, such as it gets rid of the redundant information, such as the negative frequencies, and applying the proper orthogonal decomposition or principal component analysis, as you want to call it. We can separate in these 3 main elements. I mean, the temporal coefficients, the spatial modes, and the energetic values. Well, this technique of the HPOD allows us to capture traveling waves in a complex mode, and also it has been demonstrated that the HPOD is optimal for capturing the PIV wave packets, and for the acoustic part, we suspect that it's optimal for non-stationary acoustic signals. Remember, we have the acoustic part where we have the temporal resolution because we capture at 8 kilohertz, and we have, on the other hand, the PIV measurements, and they both correlate data with the snapshots. So for each snapshot, we will have an amount of audio samples. By applying a Nelbo rule, we can determine what are the most relevant energetic modes in both sides. I mean, the acoustic and the PIV, but mainly in the acoustics, because what we are doing here is just cleaning the signals, getting rid of all the noise. While in the PIV, we apply a more aggressive truncation because we are limited to a sample frequency that I'm going to explain it later. This last equation is for noticing that the temporal modes, either for the acoustic and PIV data, they resemble. I mean, they are very, very similar. Now we have the data set. The acoustic data set is composed of the 2,880 snapshots that we have acquired by 512 audio samples. Remember that this is our temporal resolution, and by 1,024 microphones. That somehow it has the spatial information. While on the other hand, we have the PIV, the same amount of snapshots, by the x and y direction of the velocity field. And in this part, we have the spatial resolution. So we are trying to infer a vector that has a 64-dimensional vector, and we are trying to infer a vector with 8 elements in the PIV. This is the architecture that we have applied just to infer the temporal coefficients of the acoustic to the temporal coefficients of the PIV. And we have applied some normalization, activation, and regularizations just to avoid the overfitting. And we have also taken into account that the MLP doesn't recognize complex values, so we have to reconstruct the instantaneous magnitude and the instantaneous phase of the Hilbert transform, and then recombine these two elements into the magnitude and phase. Well, the MLP couldn't make it, but in the end, what we are trying to analyze is these temporal coefficients and how they behave. So let's examine what are the results of the primary wave packet reconstruction by using the spatial modes of the PIV. And here we have the temporal coefficients. By applying this reconstruction to the temporal coefficients of the PIV, we have the true column, and for the inferred column, we have the acoustic by using the acoustic side. We have analyzed for the first 4 modes, because we have this limitation in the MX array that by the Nyquist frequency, we can only hear what is happening up to 4 kilohertz. So the first mode, that more or less would be around the 0.3 structural number, we have 2000 kilohertz, to 2000 hertz. So note that the first mode is very, very appealing because it's very similar, but it switches the polarity. I mean, we have this ambiguity here, and also in the second mode. But in the third mode, we have a match, a perfect match. And this is because somehow it's learning the MLP, the phase trend, and it learns some characteristics of the flow. And for the fourth and the last case, we can see that some aliasing is very evident. But this is the progress and some conclusions that I could make so far. Also the challenges that we are facing. We have built the MX array. It's I consider it personally as a success because it's scalable, it's very cheap, it's precise, it has a synchronization in less than microseconds. We are around 10 to 20. So for our sample frequency is more than enough. And regarding the data processing, this was our first attempt. There are some parameters to tweak. The MLP probably could be improved. And well, we must detect what is actually working well and what is failing. So our next step would be using synthetic data and see what's going on with the architecture and the pipeline, for sure. These are the achievements. I could attend to and present this attempt in the Berlin beamforming conference, and also we could submit one article. It's already accepted. We are waiting for its publication, and some a course, summer school, some activities of dissemination like Noche Europea, Semana de la Ciencia, and that would be all. Thank you very much for listening.